Today I'm talking about real-time and on-chain. Really quickly, who am I? Let's see if this works. I am Billy. I am an artist and engineer from Louisville, Kentucky. I live in Germany. I got in the space with an on-chain game called Clover's Network, launched in 2019, early NFT and AMM. I launched an NFT gallery in 2021 called Folia. And for the last few years, I've been working in the Cosmos space, doing front-end dev, DevRel, running the foundation for a while, the funding, and then the product lead of the Cosmos Hub. Now I am the entrepreneur in residence at 1KX, which basically means I get to work on fun projects like this and maybe one day spin them out into companies and games. So the agenda for today, I want to talk about why we are here, what do we need, how do we get it, and then literally how do we get it, which is basically intermediate circom tips and tricks. So why are we here? We're all here under this banner of autonomous worlds, but I'd like to argue that autonomous worlds is much more than like incremental technological developments in the last few years. It's really something else. It's a movement, and there's some sort of a vibe in the middle of it. And I would like to posit that at the core of this autonomous worlds movement is actually just a commitment to make better games. You know, there's nothing that different except for we've sort of refreshed and decided like, okay, let's do it again, but let's actually make them good. Let's not sell out the games for like fast bucks. Let's not raise them. Let's just do different things so that they're actually good. You know, whatever those things may be, they might be technical incremental improvements or just really, a commitment to make them good. So I think that's a really exciting banner to get behind, but we're still missing some things. Why are games bad today? Why are they still bad? On-chain games don't have to be. But what still sucks? So there's still UX issues, keys, gas, on-ramp and off-ramp. There's limits on computation, obviously. There's limits on speeds. There's block production time and networking. So say we even push block production time all the way to the bottom. We still have networking issues. You know, if you're just as good as normal games, that's still not great. And what are the results? We're really limited in the type of games that are possible today, the types of games that exist. It's really just a subset of games, which you see a lot of turn-based games, puzzle games, which can be great games, but why limit yourself to such a restrictive subset? You know, it's like make great literature, but only inside of haikus. So what do we need? We want to increase expressivity amongst other things. And so this talk is about one of the ways to increase expressivity. Instead of being limited by these grid-based movements, which, as I said, can be great, let's just get one factor above. This is just one technique to get a little bit better, but still there's a huge phase change of improvements. You can see Mario technically being played by an AI here, but it shows every possible move at every given moment, and it just sort of explodes in complexity. So such a small change can actually increase the possibility space hugely. And how do we increase that expressivity? So the talk is called real-time and on-chain, but really what I'm talking about is a technique that a lot of you are probably familiar with, which is real-time, then on-chain. So you play the game first in real-time without limits of blockchains, and then you verify that play afterwards. And the way that I'm currently working on a model of it is that you model the game as a ZK circuit. The moves can even be private, which is another really great affordance of ZK circuits that don't necessarily need to be part of the verifiable computation. You just sort of get it out of the box. The outcome can be public and proven. If you're familiar with Yonda's battle rollup or Will Robinson, who just spoke in the other rooms, bat channels, you're definitely familiar with these ideas. So the steps to reproduce, the one-player version. First, you build a game, whatever platform you're familiar with or whatever's good for your players, and then you rewrite the core state update function of that game as a ZK circuit. You let your players play it in real time, and you basically create a keylogger for your game player. So you just record every single keystroke that they make, and there's arrows to the right. So on the right side, you could see this is like ASCII drawing of a Nintendo Entertainment System controller, and below that, it's basically guitar tabulature, which is a keylogger of every key that was pressed on the Nintendo Entertainment System controller. This is from an artwork from the 2000s from Radical Software Group, and it's an entire online catalog of one person just beating Super Mario Brothers with every single keystroke that it took to do so. I have this in a printed book, but this is essentially a formula that can just be the input to one large ZK proof to show that, yes, this person did, in fact, beat Super Mario Brothers, as long as you're able to model that inside of a circuit. So you keylog your player, you create a proof, the initial state, the keystrokes that that player made, these also can be private, and then you submit the proof of that play on chain. So there's also a two-player version. You basically get into the territory of state channels in this, in which each player's moves have to be sort of signed off by the other player. Everything else is the same, basically. The only difference is that you're probably going to get into really expensive proofs because signatures are still expensive. So the thing about off-chain computation is that it's also expensive, but in an even more annoying way. A lot of you have probably gone through the battlefield of minimizing your Solidity code to try to finally put something on chain, and that's great. All these ZK things are supposed to remove those restrictions, but you have a new set of restrictions that we get to have an entirely fun new battle going through and reducing. But there's some restraints that will make it either more or less necessary for you to make these reductions. So my goal has been to do 100% client-side proven games, which means that you have to work really within some pretty intense restrictions, but you have to make circuits that have under 1 million constraints, basically. So you're going to be working with the powers of tau 20. It's going to generate about 1 gigabyte WASM blob, and it's going to take a user about a minute to generate that proof in the browser. To compare it with EDSA signatures, there's 1.5 million constraints in verifying a single signature. So think about the complexity of that and the complexity of the games you're going to have to make in order to still prove it in the browser. There's also some techniques with doing recursive proofs, but most of those are going to require server-side provers. And if you're comfortable using the sort of growing industry of server-side proving, then you can really just let it rip in terms of complexity. So the project I've been working on is called Anybody Problem. And the thing I've learned from it is that there are mo bodies, mo problems. Essentially, this is the 3-body problem represented as 6 bodies. This is calculating the gravitational pull of each of these bodies and updating a state update. So now this is written in P5. It's a game, it's an animation, but I've recreated it as a zero-knowledge circuit. At this point, I can only run 26 seconds of the simulation of this in real world while still proving it in the browser. This is an improvement from only being able to do it with 5 seconds. And the second half of this presentation are tips and techniques of how I reduced it from 5 seconds to 26 seconds. Now, very quickly, you can realize that this simulation could also be turned into a game. If you give somebody a gun, they can shoot these things, which adds another level of complexity. Instead of 26 seconds verified, I can now only do 20 seconds. So you see the sort of adversarial environment you're working in with these sort of conditions, but it does create real-time games in a way that you can't do with state updates on a blockchain. So now's the part where I sort of grind my gears about circom, and if you're learning ZK circuits, hopefully this is useful for you, sort of a tips and tricks section. What really grinds my gears is that to write inside these applications, you're working with finite field arithmetics, which means that the biggest number you can deal with is some random number p, and everything else is modulo that p, which makes all of your calculations hard and weird. Negative numbers are just half of p, which makes them kind of weird big baby p's. So they're really weirdly large numbers that you have to constantly add p to think about where it is inside this giant thing. Yuck. There's only integers. I mean, you're probably used to that with Solidity, but also ew. Multiplication's okay, but division really falls apart a lot of the time because there's this idea of transitive properties with real numbers. They sort of stop existing or breaking down. So some math makes sense, but other math doesn't. You rely on multiplicative inverses, but that's really not what multiplication is about. It's technically that is multiplication, but realistically it's not. So what do you do instead? Oh, not to mention the constraints themselves can only have addition, subtraction, and non-quadratic multiplication. So it is an awful environment to work in, but with these tips and tricks, I think you can survive. The first thing that you want to do, because that's what I wanted to do when dealing with any sort of slightly more complicated physics, is calculate distance and calculate force. Unfortunately, both of these involve mathematics, which are not possible inside of constraint systems. So what I learned to love about circom, because Solidity wasn't painful enough, avoid negative numbers. This is the biggest thing. Stay positive. What's weird about negative numbers, as I already mentioned, they act weird. They're these huge, huge numbers, which you have to sort of think of as the difference between this big number and the largest possible number is a negative number, which actually weirdly works with addition and multiplication when you're sort of using it that way, but they're really expensive. And I say expensive because whenever you want to compare two different numbers in circom, you can't really do that. You have to convert them to their binary representation and go through one bit at a time until you decide, oh, this group of binary numbers is larger than this group of binary numbers. And so if you're dealing with this really large negative number, it's going to have up to 253 bits. So you have to go through 253 steps, and each of those steps is a constraint. And we're talking about trying to create a program that has maximum 1 million constraints. These add up really quickly when you start going into loops. So what's good to do instead is figure out the biggest possible number that any of your variables are going to have, and then offset everything from that number. So if your biggest number is 100, but it might go all the way down to negative 100, no longer. Your number is now 0 to 200. Never touch negative numbers. You've now reduced your maximum bit size massively. You've saved hundreds, if not thousands, of constraints. And when I say comparators, this is sort of applicable everywhere, not just negative numbers. You're going to want to figure out what your biggest number is in any scenario and basically like count the calories of each of them. If you can keep track of how big a number is at any given moment, you'll be able to keep track of how many bits it'll ever be needed to calculate any of these things about distance, larger than, less than. And so I made a little function here called max bits. It basically takes a number, tells you exactly how many bits you'll ever need for it. Constantly run this throughout all your programs to track exactly how big they'll be, and you'll be able to reduce the constraints needed for all the most common operations of comparators. Down here, you can see I have gravity. So gravity is 100 in this world. Gravity scaled because, we don't have decimal places. You need to offset it by the scaling factor, and then you calculate how many bits am I going to need for gravity at any given moment. So what's this all in service of? Basically, you can't do these large division or square root equations, not even large, just really simple ones. So the technique that I think carries through the biggest benefit is basically you make approximations of these. I rewrote division at a very low level. I rewrote square root at a very low level. All that's doing is basically finding an approximate version of it. But what I can also do is know what is the margin of error for any of these sorts of calculations. So here you can see distance is coming out of this approximate square root. When it's a single line, that means it's not actually being constrained. What I have to do is figure out, is this number within an acceptable range of error? And if so, then it's considered safe. So it's really a totally mind-fucked way of programming. But through these very small, weird ways of writing it, you can actually build very, very small circuits that represent quite complex state, run it off-chain, and then allow users to have a much better play experience. So that's me. I'm Billy. These are all my handles. And my last sort of question is for the app. It's actually a little bit unrelated, but I want to know about the economic commitments we're making to ensure that autonomous worlds and fully on-chain games don't suck. Is it going to make them suck as soon as there's a token involved? If you can make money with the app, will it get flooded with bots? What are the ways that we're making sure that we can produce value with these games and not get overrun by maximal value extractors? Am I a little bit early? If there's any questions, I could use the extra time for that. What do I think the answer to my question? I am fully aware of the dangers of DeFi casinos and mindless slot machines, while at the same time, I feel like random number generators are our only hope in leveling the playing field between bots and players. It's the only scenario where a bot will do just as good as a normal human, no matter how well that bot is trained. If they're really just slot machine, then you're fine. So I'd like to see some sort of a safe incorporation of random number generators so that we can embrace bots while not sort of devolving down to mindless slot machines.
So basically, I was at Zuzalu, and people were talking about guilds, like different guilds kind of acting as a middle agent for kind of protection, and you can choose to join or exit from a guild. Do you think that's kind of a safe organization you were talking about? Because I don't find it easy to imagine how that kind of organization should look like.
I'm not sure what kind of organization it's in reference to originally, though. Is this against bots?
Oh, you were saying about you were saying about random number generating.
Yeah. Oh, that's the only way that you can play a game where you're not. Oh, I was talking about maximally extractable bots.
Yeah.
Or players, basically, airdrop farmers or something coming in and, extracting as much value from the game as possible. But where do guilds is a suggestion for another solution to this is the topic at hand now?
No, I mean, I feel like there might need a middle layer of trustworthy player,
Sure. I mean, I think another way to look at that is that strong identity helps battle bots, and another way to get around strong identity is by using something like guilds to sort of semi-enforceable identity groups is where I would guess that sort of idea goes to. I think we're down to the last minute. Any last second questions? Cool. Thank you all very much.